In this example, we've got a 3 by 3 matrix and we're looking for the eigenvalues and eigenvectors. Notice that this matrix is symmetric, so we can be sure that the eigenvalues are all real and that the eigenvectors are going to be mutually orthogonal or mutually perpendicular. So let's begin the process the way we always do. We'll set up the determinant, taking lambda off the diagonal terms, and the off-diagonal terms stay the same. And we set that determinant equal to 0. When we expand this out, we get 1 minus lambda squared times 2 minus lambda. And do we have any other positive terms? All the other positive terms involve zeros, so we don't count any of them. But when looking at the determinant using the diagonals in the opposite direction, we have zeros in 2 of them, but we have one that doesn't have a 0. So we get minus 4 times 2 minus lambda, and we set that equal to 0. So to expand this, we're going to get lambda squared minus 2 lambda plus 1 times 2 minus lambda minus 8 plus 4 lambda equals 0. When I multiply this out, I get 2 lambda squared minus 4 lambda plus 2 minus lambda cubed minus 2 lambda squared. Sorry, that's plus 2 lambda squared plus 2 lambda squared minus lambda minus 8 plus 4 lambda equals 0. So now let's gather like terms. So we'll start off with minus lambda cubed, and we have a total of plus 4 lambda squared, and then we have how many lambdas? Minus 4 lambda here, plus 4 lambda there, but we have minus 1 lambda, and then we have positive 2 minus 8 is minus 6 equals 0, and that is our characteristic equation. Of the polynomial of the matrix. And now it's time for us to find the roots of that equation so that we have the eigenvalues. Now to complete this task, it's useful if you've got a sense of what some of the roots might be, and this 6 there makes me suspicious that 3 or minus 3, and I'll try 3 first. So I'm going to try guessing that one of the I'm going to start that over. I'm going to try guessing that one of the roots is 3. So I'm going to start out with lambda minus 3 out there, and then I just am going to divide that factor out of the characteristic equation. And see what we get. So first term is lambda squared, which gives us minus lambda cubed minus 3 lambda squared. Whoops, that's plus. So when I subtract that off, I get those cancel each other out, and I have only 1 lambda squared minus lambda minus 6. And so when I continue the division, I'll need to have plus lambda. When I multiply that out, it's lambda squared minus 3 lambda, and when I subtract that off, I get minus lambda minus a negative 3 lambda, which is equal to 2 lambda minus 6. And when I complete that, this worked out. So in fact, lambda minus 3 does factor out of it, and 3 is one of the roots, so I can write my characteristic equation as lambda minus 3 times minus lambda squared plus lambda plus 2. And I prefer working with out that negative sign right there, so I'm going to multiply both sides by minus 1, and that'll give me my, whoop. Now this one, I can, by inspection, find what the different roots are. So I'll have lambda minus 3, and here I'll have lambda minus 2 times lambda plus 1, so that my roots are 3, 2, and minus 1. And these are also the eigenvalues of the matrix. So those are my 3 eigenvalues. Corresponding to each eigenvalue is an eigenvector, and now we'll begin the process of finding the eigenvector that corresponds to each of these eigenvalues. We're going to do this by taking minus lambda off the diagonal terms and solving a system of equations. So the system of equations that we're going to solve is always 1 minus lambda 2, 0, 2, 1 minus lambda, 0, 0, 0, 2 minus lambda, and we'll want the 3 components of our eigenvector, and we set that equal to the 0 vector. Now, for the first case, for lambda equals 3, our first eigenvalue, that gives us a system of equations if I write them in the augmented matrix form of minus 2, 2, 0, 0, 2, minus 2, 0, 0, 0, 0, 2 minus 3 is minus 1, 0. And when I apply Gaussian elimination to this, all I need to do is replace row 2 by the sum of row 1 and row 2. I get minus, row 1 stays the same, minus 2, 2, 0, 0. This is the sum of, the next row is the sum of the old row 1 and the old row 2, or 0, 0, 0, 0. And row 3 remains the same, 0, 0, minus 1, 0. From this last equation, we know that minus x3 is equal to 0, and this tells us that x3 must be equal to 0. And when we look at the first equation, we see that minus 2x1 is equal to minus 2x2, or x1 is equal to x2, and we have an eigenvector equal to x3 is 0, x2 is arbitrary, so we'll choose it as 1, and then x1 is going to be equal to whatever we chose for x2. So that is the eigenvector for lambda equals 3. And we always need to make it very clear which eigenvector goes with which eigenvalue. So we've solved for the first eigenvector, time to go for the next one, and our next eigenvalue was 3, so now our next eigenvalue was 2, so we'll take 2 off the diagonal and set up our system of equations. So for lambda equals 2, we'll have 1 minus 2, or minus 1, as the first term. In our next row, we have 2, 1 minus 2, or minus 1. And then we have for our last row 0, 0, and then 2 minus 2, or 0, as our system. In our next step of Gaussian elimination, what we're going to do is we're going to take row 1 and keep it the same. And then for row 2, we're going to eliminate the 2 that leads off this row by taking 2 times the old row 1 and adding it to row 2. So we have 2 times minus 1 plus 2 gives us 0. Then we have 2 times 2 gives us 4 minus 1 is 3. And then 0, 0. And the last row contains no information. So what this tells us is that from row 2 we get 3x2 is equal to 0, or x2 is equal to 0. From row 1 we get minus x1 plus 2x2 equals 0, or x1 is equal to 2x2, but we know that x2 is 0, which tells us that x1 is also 0. Now, do we have any information about x3? No. So in fact, x3 is arbitrary. The other two values are 0. So our eigenvector is 0, 0, 1 for the eigenvalue of 2. So we have 2 of the eigenvectors. We have only to find the third one, and now we'll begin looking for it. And here our eigenvalue is equal to minus 1, so we'll subtract minus 1 from each of the diagonal terms, which is going to give us a system of equations 1 minus a negative 1, or 2, 2, 0, 0. The next row is 2, 1 minus a negative 1, 2, 0, 0, 0, 0, and this is 2 minus a negative 1, 3, 0. So when we perform Gaussian elimination on this, we get 2, 2, 0, 0, 0, 0, 0, 0. Next row is full of zeros. And our last row is 0, 0, 3, 0. From this last equation, we get that x3 is equal to 0. And from the first equation, we learn that x1 is equal to minus x2. And picking x2, so we know x3 is 0, picking x2 arbitrarily to be 1, we know that x1 is 1, and that's the eigenvector for lambda equals minus 1. So we found our 3 eigenvalues and our 3 eigenvectors for this 3 by 3.